So we have entropy, it's symbol S, right? And the concept of entropy is quite confusing and also not at the exact same time. So the concept of entropy is that in the world, entropy always increases. People think of entropy as a measure of disorder. So like if you look at my desk, like as time goes on, right? Like here's my desk, right? It's disordered. It's like the pad of paper is not straight, right? There's like stuff all around, and the disorder will naturally increase with time unless I go ahead and do work to fix it, which I'm not gonna do. But it becomes sort of hard to think about that definition when you're trying to think about like a container, those are ice cubes, versus like water, and you're like, which one of those has more disorder? You have to have a molecular understanding of solids and liquids to know which system would have more disorder. So another way to think about the level of disorder is thinking about all the motion of the particles. So higher temperature objects, if T is higher, then the disorder is more, right? In a certain object, just generally thinking. And if everything's moving around more, the temperature's more, the kinetic energy's more, right? That velocity's more. So when you compare like the ice cubes and the water, it's hard for your mind to be like, I don't know, like the same order to me. So if you can't know, it's based on temperature, on which one will have more entropy. Things naturally go to a state with the highest entropy, not a thing in particular, an entire system. So even though one object might change its entropy to decrease, become more organized, the overall system, the overall world, that change, unless it's made by a human, if that's a natural change, it'll go to make the whole system increase in entropy. The change in entropy is also a great indicator of time direction. So like a great example is if you like throw a bunch of paper, right, or things all at you, like just like you know that those things are never going to just magically come on the desk into your hand, right? So entropy also works as an arrow of time, letting you know which way something happened. So if you watched a video, I put 3 cool videos up for you in the lesson. They're just YouTube videos made by other people. And one is a song. It's quite catchy, Arrow of Entropic Time. And it does a lot of videos that you know are backwards. And you know they're backwards because they don't match up with what we see in everyday life, which is that things naturally go towards disorder, not order. So that's what happens when people talk about entropy and time. There are 2 ways to mathematically calculate an entropy. So if you want to know how entropy has changed, you can think about the heat change over a certain temperature. Should have deltas there. I made this new this year. But that's good. It's an approximation. I really need some calculus because obviously if temperature is reaching a new temperature, it's changing along the way. But that's fine. It's a general just estimate. Another way to think about it is actually looking at the number of microstates. This is something you would do in upper level thermal class. What's going on here is it basically says the more options that you have, the more disorder there is. This is the constant we've been using all along, Boltzmann constant, the same one we've been using this whole time, whatever that is. And so the concept of this basically is if you flip 10 coins, right? And you keep flipping them over and over and over and over and over again, the most disordered state would be the one where it's equal number of heads and equal number of tails. Why? Because there's the most options with that. If a coin comes out as all heads, there's only one way. Everything must be a head for that to happen. If it's all heads but one tail, there's not that many ways for that to happen, right? It could be like this one, or this one, or this one. So there's only like 10 ways that could physically happen. And so as you approach, now if you have 8 heads and 2 tails, right, then you're getting this, oh, well, it could happen that, oh gosh, these 2 are tails, or 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 these 2, or these 2. And you start to see that more and more options come out about how the coins could lay out on the desk, which coin comes out. And the most of those happen at 50-50. And so that's why it's the most probable state, because the most probable state is highest entropy. This is something that we don't need to understand in this level of physics, but it's cool. And I posted a video on it, so you can look at it more in terms of that kind of discussion of micro states, the way things can be organized. But it's extra. It's neat, though, so I figured I'd mention it. Okay, so this kind of leads us to the second law of thermodynamics. That basically says anything that just happens naturally, like ice melting, is going to lead to an increase in the system's entropy. spontaneous flow of energy will stop in equilibrium. So when everything's room temperature, that's equilibrium. Same like when things fall, right? They just stop when they're in equilibrium. Same idea. And then somebody, I don't know who it was like, damn, equilibrium seems like really important. We probably should have made a law on that. They didn't want to make it the third law because it's like probably should have come before even the first law. Like, add heat and work to change energy. Well, like, what would the energy be? Of this water bottle, it's just been sitting here for days. It's at equilibrium. So they're like, okay, let's make it the 0th law. So we don't have to renumber anything. We just make it come first. And that's pretty creative. So if you hear someone talk about the 0th law, it's basically the backtracking of, we should have said that like things are in equilibrium if they just be chilling. So how does heat move? Heat moves from hot things to cold things, and it stops moving when they're in equilibrium. And that is like very fundamental, and it's something we really understand well. Right? Ice melts to become room temperature. Ice doesn't get colder as you leave it in the glass. But that would be a great invention if you can make that. So I put some objects at different temperature. I got some ice cubes. I'm going to put them in some tea. I don't know why. You would never want to do this. I like my tea boiling hot, but it's fine. So take the ice cubes and I put them in the tea. So the entropy of ice itself, does the ice increase in entropy or decrease in entropy? So the entropy of the ice increases. Yes, very nice job, team. I like the up arrow. Little carrot. Okay, so the ice does increase in entropy. So ice is good. It does what it's supposed to. I think it's supposed to increase as time goes on, and it does. But you think about the T, and you think about the delta S of the T, and you're like, oh, the T gets colder. The molecules slow down. That party stops being so crazy. Like, oh, whoa, the T decreases. And so that's where our equation of the ratio of temperature being on the bottom lets us know that the ice increase is mathematically more entropy change than the T. And I've never seen AP ask this mathematically, only conceptually, understanding that as systems blend together, entropy will increase. Just kind of a general knowledge of which way heat flows. So heat flows in the system from what to what? Heat flows from, and you're like, okay, heat always goes from hot to cold is what you should be thinking. So heat flows from the T to ice, right? Thus, the ice gets some entropy and the T loses. So molecules in the T start bumping around, moving molecules in the ice, right? And so the ice, everything is getting a little more crazy in the ice, but everything's getting a little less crazy in the T. But overall, the craziness of the whole system has to increase. And that's how mathematically it happens. So heat flows, stuff bumps, stuff is bumping, right? Parties bumping. Good. And then on the paper are just some other examples of entropy that you can think about. So if you have like a ball bouncing eventually comes to rest, that's equilibrium, right? A ball will never start bouncing on its own. So equilibrium also relates to the lowest possible energy. Because like work, I don't know how to say this without calculus, but like the lowest energy something can possibly have is when it's in equilibrium, and that's the most probable state. That's where entropy will be the highest. So that's cool. So that's our basic takeaway. We now know the first law. That's about adding energy. We know the second law. It's about the way processes will happen so that they'll always reach this equilibrium, which means entropy increases. And then we're like, oh yeah, equilibrium is the most probable state. Back up, 0th law. So we know three laws plus ideal gas law.